So now let's look at shear stresses in a shaft. So remember, shear stresses, unlike normal ones, are not stresses that are applied along the axis. They're going to be sliding across the surface, so almost 90 degrees off of what a normal stress would be. So let's go over here and get out of red. Now remember from last week's set of lectures, we had developed an equation that said that, okay, well, we looked at it and the torque in the shaft was going to be equal to the integration over the area of all the shear stresses times rho, which is the radius at which where these elements were located. And so if we integrated all these little individual shear stresses across the entire area, we'd find out the input torque. Just like for normal stress, where if we integrate all of the normal stresses over the area, we would get the input load. Now, let's assume, and this is the important thing, that we are in the linear elastic region. So once we're in the linear elastic, let me try that again. Once we are in the linear elastic region, we will be able to use Hooke's law for shearing strain, which, if you remember, is very similar to Hooke's law for normal strain, which is just the shear stress is equal to the modulus of rigidity times the shear angle. Now, the important thing to remember with this is that this is only for only for the linear elastic region. If we go beyond the linear elastic region, then this no longer applies. So if we plastically deform it, all these equations that we're about to set up are not going to work. Now, I do want to bring back another equation from last week, and it deals with that shear angle, because we said, okay, the shear angle relates to the maximum shear angle by this equation. So the shear angle is going to equal to the radius where we're calculating the shear angle divided by c, where c in the case of a shaft is going to be the outside radius. But in general, c is the distance from our neutral axis to our outside surface times that maximum shear angle. So I wanted to bring that up because what I like to do, if we take this and just multiply both sides by g, we'd have g gamma is equal to rho over c g gamma max. And as long as we're within the linear elastic region, then we'd be able to say, okay, well, that's the shear stress is going to be held to the same relationship as the shear angle, where we can find the shear stress at any point within the shaft is just going to be a ratio of the angle, the radius at which it's at divided by the c, which is that distance from the neutral axis to the outside edge, the outside radius of our shaft. Now, but what this also tells us is that the shear stress is changing within our shaft. Let's go take a look at, if I plot this out. So this would be the typical idea of the way shear stress is going to vary within a shaft. In the center, which is the radius equals 0, so if I look at my equation that I said, okay, shear stress is the radius divided by the outside times the max. Well, when rho is 0, so right here, my shear stress will be 0, because shear stress will be 0 over c, whatever, 0. As we move through here, it increases until it hits c, because if I take a look at that, I plug in c for rho, c over c is 1, so my maximum shear stress is going to be at the c. Now, this also applies for hollow shafts, where it doesn't start at 0, but it starts at c1. Because once again, remember, c is the distance to the outside surface. So in a shaft, you'd have, a C1 and C2 would mean the inside surface and then the outside surface. So the minimum will be at the inside surface because that's the smallest. So let's just, from there, let's step back here because I've got room to write here. And so now I have these, I've got this guy and then this one right here. We'll label this 1. This is the one that we pulled from our other lecture. And then what we've got here, we'll call this one 2. And so now what we're going to do is I just want to take, and let's use a highlighter. I want to take this equation from 2 and plug it in here for 1. And so now if I do that, what do I have? Well, that tells me that my torque, I've still got the integration over the area of rho. Now I've got rho over c, tau max dA. Why did I want to rearrange this equation in this way? Because I want that shear stress max. And the shear stress max, usually when we're dealing with this stuff, what we care about is the maximum. Why? That's where it's going to break. And that's what we're concerned with. So now if I take a look at this and I can start pulling some of the stuff outside of the integration symbol, well, C isn't dependent on the area, so we can pull that out. Tau max isn't dependent on the area, but those rows are. So what I'm left with is tau max over C is equal to the integration of rho squared over the area. And you may remember what this is from earlier classes, because now that I'm looking at the radius squared and I go over the area, what is that? Well, if we remember, this is our polar moment of inertia. So this is a area property from our statics classes, and we call that J. And so J is something that we can look up typically in our textbook or the engineering equation manual to find out what the polar moment of inertia is. And so what that brings us to is that tells us that torque is T max times J over C. Now, typically, what we're doing is we're looking for what the shear stress is. So we rewrite this as the maximum shear stress in a shaft is going to be TC over J. And that's our equation. Now, if we wanted to find the shear stress at any position, all we would do is replace that C with a rho and say the shear stress at any one point is T rho over J. And that will be able to calculate out whatever we need to do. And so this is how we'd find the maximum shear stress in a shaft by knowing the geometry and the torque.